What if I told you that the ground beneath your feet isn't really solid? What if I told you that the moment you just experienced, this very second, the one you're living in right now, might not exist in the way you think it does? What if time itself, the invisible river you've been swimming in your entire life, is nothing more than a magnificent illusion? And what if space, the endless canvas on which every star, every planet, every atom of your body is painted, is not a backdrop to the universe but something stranger, something more alive, something that bends and breathes and tears apart in ways that would make your mind reel if you truly understood them? These aren't the musings of a philosopher sitting in a candlelit room. These are the conclusions of the greatest scientific minds in human history. Einstein, Hawking, Feynman, Gödel, brilliant, obsessive, sometimes tortured thinkers who spent their lives chasing the edges of reality and came back with answers that raised even more terrifying questions. Because here's the thing about paradoxes: they don't just challenge your assumptions. They pull the rug out from under the entire floor. They make you question not just what you know, but whether knowledge itself is even possible. A paradox is not simply a contradiction. A paradox is a crack in the foundation of logic, a place where the universe seems to be saying, "You thought you understood the rules? Watch this." And the paradoxes of time and space are unlike any others. They are not puzzles you can solve with a calculator. They are not riddles that have neat, satisfying answers waiting at the end. They are windows into the deepest, most unsettling truths about the nature of reality. Truths that, once seen, cannot be unseen. So take a breath. Hold it for a moment. Feel the air filling your lungs, the weight of your body, the passage of the second into the next. Because by the time this journey is over, you may never experience time and space the same way again. Let's begin. Imagine you are standing at the edge of a cliff. Below you is not a valley or an ocean, but the entirety of the past. Every moment that has ever happened, every battle ever fought, every word ever spoken, every heartbeat of every creature that has ever lived, all of it piled up beneath you like geological strata. And above you, stretching into a sky that has no ceiling, is the future. Every possibility, every path, every choice that hasn't yet been made, shimmering like heat haze above an asphalt road in summer. And you are standing at the very thin, razor-sharp edge of the present. The now. The moment. But here is the first crack in the floor. Physicists will tell you, with mathematical certainty, that the present moment, the now, has no thickness. It has no duration. It is an infinitely thin line between what has already happened and what hasn't happened yet. And if it has no thickness, no duration, then in what sense does it exist at all? This is not a trick question. This is not a game of words. The mathematician and philosopher Zeno of Elea, who lived in ancient Greece around 450 BCE, was one of the first recorded thinkers to notice that time and motion, when examined carefully, seemed to dissolve into absurdity. And he came up with a series of paradoxes that have haunted mathematics, physics, and philosophy ever since. Paradoxes so elegant in their simplicity and so maddening in their implications that more than 2,000 years of human thought have not fully resolved them. Zeno's most famous paradox is the one about Achilles and the tortoise. You've probably heard a version of it. Achilles, the greatest warrior of ancient Greece, agrees to race a tortoise. Being sporting, or perhaps overconfident, he gives the tortoise a head start of, say, 100 meters. The race begins. Achilles, being vastly faster, quickly covers the 100 meters and reaches the point where the tortoise started. But by the time he gets there, the tortoise has moved forward a little, let's say 10 meters. So Achilles runs those 10 meters. But by the time he covers them, the tortoise has moved forward again, 1 meter. Achilles covers that meter. The tortoise has moved a centimeter. And so on, forever. No matter how small the gap becomes, the tortoise is always ahead. Logic, pure, rigid, unforgiving logic, seems to say that Achilles can never catch the tortoise. And yet, of course he does. Of course he wins the race. We all know that. We can see it. We can time it with a stopwatch. And yet Zeno's logic is airtight. Every step is valid, and the conclusion is impossible. Stop for a moment and ask yourself, if this argument is logically valid, and the conclusion is obviously false, then something must be deeply wrong with either our logic, our mathematics, or our understanding of space and time itself. Which do you think it is? The ancient Greeks didn't have an answer. It took more than 2,000 years, and the invention of calculus by Newton and Leibniz in the 17th century, to provide a mathematical framework that could handle infinite series converging to finite values. In calculus, the infinite sum of 100 plus 10 plus 1 plus 1/10 plus 100th, and so on, equals a finite number, 111.1, repeating. Motion is possible. Achilles wins. Problem solved. But is it really solved? Because the deeper question, not the mathematical one, but the philosophical one, lingers like smoke after a fire. The question isn't, can we sum an infinite series? The question is space actually made of infinitely divisible points? Is time actually made of infinitely divisible moments? And if it is, then motion, real physical motion, requires traversing an infinite number of points in a finite amount of time. Every step you take, every breath you draw, every heartbeat, you are, in a very real sense, performing an infinite number of tasks just to walk across a room. Doesn't that stop you in your tracks? Now, modern physics has something interesting to say about this. There may be a minimum length in the universe, a smallest possible unit of distance below which the concept of space simply ceases to have meaning. It's called the Planck length, named after the physicist Max Planck, the founder of quantum theory. The Planck length is approximately 1.6 times 10 to the power of -35 meters. That is so incomprehensibly small that if you scaled a proton, already a billionth of a meter, up to the size of the observable universe, the Planck length would be roughly the size of a proton in that comparison. If the Planck length is the true minimum unit of space, then space is not infinitely divisible. It is, at its smallest scale, granular, pixelated, like a photograph that, when zoomed in far enough, resolves into individual dots. And if that's true, then Zeno's paradox dissolves, not because of calculus, but because there is no infinite regression. Space has a bottom. But here's where it gets stranger. If space is pixelated, then what are those pixels? What is the fabric of space made of? And if there is a minimum unit of space, is there also a minimum unit of time? There is. It's called the Planck time, approximately 5.4 times 10 to the power of -44 seconds. It is the time it takes light, traveling at the maximum speed the universe allows, to cross one Planck length. Below this scale, our current physics breaks down entirely. We have no equations, no theories, no models that can describe what happens in spaces smaller than the Planck length or in durations shorter than the Planck time. It is the edge of the map. Beyond here, there be dragons. And yet those dragons might hold the answer to everything. Now let's talk about time. Because time, it turns out, is far weirder than space. At least space sits still, more or less. Time moves. Or does it? This is one of the most profound and disorienting questions in all of physics. Does time actually flow? Or is the sensation of time passing, the feeling of moments sliding from the future through the present into the past, entirely an illusion created by our minds? Albert Einstein, in a letter written to the family of his lifelong friend Michel Besso, who had just died, wrote these words, "Now he has departed from this strange world a little ahead of me. That means nothing." People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. Think about what he's saying. Einstein is not being poetic. He is not trying to comfort a grieving family with beautiful words. He is making a physical statement about the nature of reality. The past is not gone. The future is not waiting. The present is not special. According to the mathematics of relativity, all of time, every moment that has ever existed or will ever exist, exists simultaneously in what physicists call a block universe, or the eternalist view of time. The technical term is the block universe model, and it comes directly from the equations of special and general relativity. Imagine a loaf of bread. The whole loaf exists all at once, even though you can only see one slice at a time when you cut into it. Now imagine that the loaf is the entire history of the universe, from the Big Bang to the final cold death of all stars, and that each slice is a moment in time. All the slices exist simultaneously in the loaf. You, as a conscious being, are a very thin slice moving through the loaf, or rather, you're not moving at all. The feeling of moving is just your consciousness illuminating one slice at a time, creating the illusion of flow. Every moment of your life, your first breath, your happiest memory, the moment you are experiencing right now, and the moment of your death, all of these exist simultaneously in the block universe. They are all equally real. The past is not over. Your childhood isn't gone. In the physics of space-time, it still exists, frozen in amber, real and solid and permanent, just as inaccessible to your future self as a city on the other side of the world is inaccessible to you right now. Pause here. Ask yourself, if the block universe is real, if every moment of your life already exists, fixed and permanent, then what does it mean to make a choice? What does free will mean in a universe where the future already exists? This is one of the most agonizing intersections of physics and philosophy, and we will return to it. But first, let's push deeper into the strangeness of time itself. One of the most mind-bending facts about time is something that Einstein proved, and that has since been confirmed by experiment more times than we can count. Time does not pass at the same rate everywhere. This is not a metaphor. This is not a feeling or a perception. It is a measurable, quantifiable physical fact that two clocks, real, physical, atomic clocks, placed in different locations or moving at different speeds will record different amounts of elapsed time. This is called time dilation, and it comes in two flavors: velocity-based and gravity-based. Velocity-based time dilation, from Einstein's special theory of relativity, says that the faster you move through space, the slower you move through time. If you are on a rocket ship traveling at 90% of the speed of light, time on your ship will pass significantly slower than time on Earth. If you go fast enough, close enough to the speed of light, you could leave Earth as a young person, travel to a distant star and back in what feels to you like a few years, and return to find that decades or centuries have passed on Earth. Everyone you knew is dead. The world has changed beyond recognition. And you, the traveler, are still young. This is the famous twin paradox. One twin stays on Earth. The other boards a spacecraft, travels at near light speed to a distant star, and returns. When they reunite, the traveling twin is younger than the one who stayed home. Not just feels younger, is biologically, physically, genuinely younger. Less time has actually passed for them. And here is the crucial point. This has been experimentally verified. Not in the dramatic, cinematic sense of human twins in spaceships, but with atomic clocks, the most precise timekeepers ever built. In 1971, physicists Joseph Haffel and Richard Keating put atomic clocks on commercial airplanes flying around the world and compared them to identical clocks left on the ground. When the planes landed, the airborne clocks had recorded slightly less time than the ground clocks, exactly the amount predicted by both special and general relativity. The effect was tiny, a few hundred nanoseconds, but it was real. Time really does pass differently at different speeds. GPS satellites depend on this understanding. The atomic clocks on GPS satellites are moving fast enough relative to Earth, and high enough in Earth's gravitational field, that without corrections for relativistic time dilation, GPS systems would accumulate errors of about 11 kilometers per day. Your navigation app would be useless. Every GPS calculation you've ever made has been saved from catastrophic error by the equations of Einstein's relativity, which means you have personally in your everyday life, been saved by the counterintuitive physics of time dilation, even if you never knew it. But velocity is only half the story. The other flavor of time dilation comes from gravity, as described by Einstein's general theory of relativity. Gravity doesn't just attract masses, it warps space-time itself. Massive objects, stars, planets, black holes, curve the fabric of space-time around them, and this curvature affects not just the paths of moving objects but the passage of time. The stronger the gravitational field, the slower time passes. This means that time passes slightly faster at the top of a tall mountain than at sea level. The difference is minuscule, billionths of a second per day, but it is real and measurable. It means that time at the surface of the sun passes slower than time here on Earth. And it means that near a black hole, one of the most extreme gravitational environments the universe can produce, time can slow to nearly a standstill as observed by someone watching from far away. Picture this. You are orbiting a black hole in a spacecraft, just outside the event horizon, the point of no return. Your engines are roaring, fighting the black hole's gravitational pull with everything they have. From your perspective, everything seems normal. You're doing your job, checking instruments, drinking coffee. An hour passes. But from the perspective of someone watching you from a safe distance, from Earth, say, what they see is completely different. Because time near the black hole is so profoundly dilated, your 1 hour corresponds to years, perhaps centuries, on Earth. If you looked back at Earth through a sufficiently powerful telescope, you would see centuries of history unfolding in fast forward. Generations being born and dying, civilizations rising and falling, all while you drink a single cup of coffee. And if you were to fall into the black hole, cross the event horizon, the distant observer would never see you do it. To them, you would appear to slow down, redden, and freeze at the edge of the black hole for eternity, as time for you, from their perspective, dilates to infinity. To you, falling in, you would cross the event horizon in a finite and perhaps short time. You might not even notice the moment of crossing. But beyond the event horizon, no signal, no light, no information of any kind can escape to the outside universe. You are effectively cut off from the rest of reality. The universe outside has been sealed away from you by gravity. This brings us to one of the most mind-bending paradoxes in all of physics, the black hole information paradox. And to understand it, we need to understand something about the nature of information itself. In physics, information is not just data on a hard drive. Information, in its deepest sense, is the state of a physical system. Every particle, every quantum of energy, its position, its spin, its momentum. The laws of physics, particularly quantum mechanics, state that information cannot be destroyed. This is a fundamental principle, as bedrock as the conservation of energy. If you burn a book, you might think the information in it is lost. But in principle, if you could track every molecule of smoke, every photon of heat, every ash particle, you could reconstruct the original book. The information is still there, scrambled, but present. What happens when something, say an encyclopedia, or a star, or your entire body, falls into a black hole? Stephen Hawking, in 1974, made one of the most shocking discoveries in the history of theoretical physics. Black holes are not entirely black. They emit a faint glow of thermal radiation, now called Hawking radiation, produced by quantum effects near the event horizon. And over vast stretches of time, truly incomprehensible timescales, a black hole will emit enough Hawking radiation to gradually lose mass and eventually evaporate entirely, disappearing in a final burst of energy. And here is the paradox. Hawking radiation, as Hawking originally calculated it, is completely random. It carries no information about what fell into the black hole. It's thermal noise. It's as if you threw the encyclopedia into the black hole, and what came out was the equivalent of random static. The information, every word, every sentence, every idea in that encyclopedia, would be irretrievably gone, destroyed. But that violates one of the most fundamental principles of quantum mechanics. Information cannot be destroyed. So which is right? Quantum mechanics or general relativity? For decades, this was considered one of the most important unsolved problems in physics, and Hawking himself changed his position on it multiple times. In 2004, he conceded, at a famous conference in Dublin, that he had been wrong, that somehow information must escape the black hole. But how? The mathematics of how information could escape Hawking radiation without violating the structure of general relativity remain one of the deepest unsolved puzzles in physics. One of the most extraordinary proposed solutions is called the holographic principle, and it is one of the most mind-warping ideas in modern physics. The holographic principle, developed largely by physicist Juan Meldacena in 1997 and building on earlier work by Gerard T. Hooft and Leonard Susskind, suggests that all the information about the three-dimensional interior of a volume of space can be encoded on the two-dimensional boundary of that region, the surface. Think about what this means. A hologram is a two-dimensional surface that encodes a three-dimensional image. The holographic principle says that our entire three-dimensional universe might be, in a deep physical sense, a hologram, a two-dimensional encoding of information projected into three dimensions. Everything you see, touch, feel, everything in your perceived three-dimensional world might be a projection from a two-dimensional surface at the boundary of the universe. This is not science fiction. This is not metaphor. Meldacena's paper on this, the AD/CFT correspondence, is one of the most cited papers in the history of physics. The mathematical framework is real, rigorous, and has led to breakthroughs in understanding not just black holes but also quantum chromodynamics, the physics of strongly interacting particles. Ask yourself this: if our universe is a hologram, if reality is a kind of projection, does that change your sense of what is real? Does it make your experiences less real? Or does it make you wonder what the screen the universe is projected on actually is? And this leads us to another paradox, one that strikes even closer to home. Closer than black holes. Closer than distant stars. In fact, it's right at the heart of quantum mechanics, the theory that describes the behavior of particles at the smallest scales, and it is called the measurement problem, which encompasses one of the most famous thought experiments in all of science, Schrödinger's cat. In 1935, the Austrian physicist Erwin Schrödinger devised a thought experiment that was meant to expose the absurdity of quantum mechanics when applied to everyday objects. Quantum mechanics says that a particle, before it is observed, exists in a superposition of all possible states simultaneously. An electron can be spinning clockwise and counterclockwise at the same time, until you measure it, at which point it chooses one or the other. This is not a statement about our ignorance. It's not that we just don't know which way the electron is spinning. The electron genuinely is in both states simultaneously, until the act of measurement forces it to commit to one. Schrödinger thought this was absurd, and he devised his famous thought experiment to make the absurdity vivid. Imagine a cat in a sealed box. Inside the box is a tiny amount of radioactive material, a Geiger counter, a vial of poison, and a hammer connected to the Geiger counter. If the Geiger counter detects a radioactive decay, which is a quantum event governed by quantum randomness, the hammer smashes the vial, the poison is released, and the cat dies. If no decay is detected, the cat lives. Quantum mechanics says that before you open the box, the radioactive material exists in a superposition. It has both decayed and not decayed, which means the Geiger counter has both detected and not detected an event, which means the hammer has both fallen and not fallen, which means the vial is both smashed and intact, which means the cat is both dead and alive, simultaneously. It is only when you open the box, when you make an observation, that the superposition collapses and the cat is either alive or dead. Schrödinger intended this as a reductio ad absurdum, a proof by contradiction that quantum mechanics, whatever it says about particles, cannot be literally true about macroscopic objects like cats. But the response of many physicists was not, "You're right. Quantum mechanics needs to be fixed." The response was, "Yes, That's exactly what quantum mechanics says, and it applies to everything, including cats. The question of what causes the collapse of the quantum superposition, why we never see a cat that is literally both alive and dead, is one of the deepest unsolved problems in all of physics. It is called the measurement problem, and there are multiple competing interpretations of quantum mechanics, each more bizarre than the last, each trying to answer this question. The Copenhagen interpretation, the most widely taught, says, "Don't ask what's happening before you measure. There is no fact of the matter. Only the measurement result is real." The wave function, the mathematical object that represents the superposition, is not a physical thing. It's a tool for calculating probabilities. But this feels deeply unsatisfying to many physicists. It puts the observer, the measurer, at the center of reality in a way that seems to make physics dependent on conscious beings. And that leads to even stranger questions. What counts as an observation? Does it need to be a conscious being? Can a rock observe a particle? One interpretation that sidesteps the collapse entirely is the many worlds interpretation, proposed by Hugh Everett III in 1957. In this interpretation, there is no collapse. The superposition never ends. Instead, when a measurement is made, the universe splits into two branches, one in which the cat is alive and one in which the cat is dead. Both branches are equally real. Both continue to exist, evolving forward in time. You, the observer, in one branch see a living cat. The other version of you sees a dead cat. Neither of you knows about the other. In the many worlds interpretation, every quantum event that has multiple possible outcomes causes the universe to branch. Every second, the universe is splitting into a stupefying number of parallel realities, each equally real, each proceeding independently. The universe is not one history, but an almost incomprehensibly vast tree of branching histories. If many worlds is correct, then right now, there exist versions of you who made different choices at every decision point in your life. Every time you faced a choice, and quantum randomness played even an infinitesimal role in your neural processing, and it may play a significant role, the universe forked. Another you took the other path. Another you has a different job, a different relationship, a different life. And all of those versions of you are equally real. Take a moment with that. Not as a comforting fantasy or a disturbing nightmare, but as a genuine scientific hypothesis supported by some of the most eminent physicists in the world, including Stephen Hawking, who was sympathetic to many worlds, and David Deutsch, one of the pioneers of quantum computing, who considers it the only sensible interpretation. Now, here's a question worth sitting with. If the many worlds interpretation is true, does your life, your choices, your sacrifices, your struggles mean less? Or does it mean that the particular you who has made the particular choices you have made is a unique thread in an infinite tapestry, valuable precisely because of its specificity? But let's leave quantum mechanics for a moment and return to the large scale, to the cosmos itself, because there are paradoxes there that are equally staggering, and they involve not the very small but the very vast. The universe is expanding. This has been known since Edwin Hubble's observations in the 1920s, when he discovered that distant galaxies are moving away from us, and that the farther away a galaxy is, the faster it's receding. This led to the Big Bang Theory. The universe began as an incredibly dense, incredibly hot singularity about 13.8 billion years ago and has been expanding ever since. But here's something that almost no one stops to think about properly. The expansion of the universe is not galaxies flying outward through space. The galaxies are not moving through space like bullets through air. The space itself is expanding. The fabric of space, the medium in which all things exist, is growing, stretching, increasing in volume. Galaxies are being carried apart by the expansion of space the way dots on the surface of an expanding balloon move apart from each other. Not because the dots are moving, but because the rubber between them is stretching. Now, here is a paradox that emerges from this. If space can expand, if space itself can grow and stretch, what is it expanding into? What is outside the universe? This is a question that sounds simple and childlike, but it is actually one of the most profound questions in all of cosmology. And the answer that physics gives is not satisfying in any ordinary sense. There is no outside. The universe is not expanding into anything, because the universe is, by definition, everything that exists. Space is all there is. There is no exterior. But wait, if the universe has no edge, no boundary, no exterior, then how can it be expanding? Expansion implies getting bigger. Getting bigger implies there's more space where you weren't before. How can space itself be more without there being something for the new space to exist within? One way to think about it, though all analogies eventually break down, is to use the balloon again. But now imagine you are a two-dimensional creature living on the surface of the balloon. Your entire universe is the surface of the balloon. You can travel in any direction on the surface. There is no edge to your universe. It's finite but unbounded, like the surface of a sphere. When the balloon expands, your two-dimensional universe gets bigger. Distances between points on the surface increase. But from your two-dimensional perspective, there is no outside. The interior of the balloon and the exterior of the balloon don't exist in your universe. They're not part of your reality. The expansion of the surface is a self-contained fact about your two-dimensional universe that requires no reference to anything outside. Our universe may be analogous to this, but in 3 dimensions, a 3-dimensional surface of a 4-dimensional object. The outside doesn't exist in our 3-dimensional universe because we can't perceive or access the 4th spatial dimension in which the analogy would play out. This is deeply disorienting. And here is what makes it even more so. The expansion of the universe is accelerating. Not just expanding, accelerating. This was discovered in 1998 by 2 independent teams of astronomers, led by Saul Perlmutter and Brian Schmidt, who won the Nobel Prize in Physics in 2011 for this discovery. They were studying distant supernovae, exploding stars, using them as standard candles to measure cosmic distances. And what they found was that distant supernovae were dimmer than expected, which meant they were farther away than expected, which meant the universe was expanding faster than it should be if it were only driven by the initial momentum of the Big Bang. Something is causing the expansion to accelerate. Something is pushing space apart with an energy that pervades all of space uniformly, that doesn't dilute as space expands, that has no apparent source or cause. This mysterious something is called dark energy, and it comprises approximately 68% of the total energy content of the universe. We have absolutely no idea what it is. Dark energy is not dark because it's evil or mysterious in a metaphorical sense. It's dark because it doesn't interact with light or with ordinary matter in any detectable way. It is invisible, undetectable except through its gravitational effects on the expansion of the universe. And despite comprising most of the universe's energy, we have no theory that adequately explains it. Some physicists think it might be a property of empty space itself, a vacuum energy. Though when quantum field theory attempts to calculate what this vacuum energy should be, the answer it gives is off by a factor of 10 to the power of 120. That is, the theoretical prediction is not just slightly wrong. It is more wrong than any other prediction in the history of science, by an almost inconceivable margin. Physicists sometimes call this the worst prediction in physics, and it points to a catastrophic gap in our understanding of how quantum mechanics and gravity interact. But dark energy is only one of the mysteries hidden in the darkness of the cosmos. An even larger fraction of the universe, about 27% of its total mass energy content, is made of something called dark matter. Dark matter is not dark energy. They are 2 different mysteries. Dark matter is matter, something with mass, something that exerts gravitational pull on other things. But it cannot be detected because it doesn't emit, absorb, or reflect light. It is gravitationally present but visually invisible. The evidence for dark matter is overwhelming and comes from multiple independent lines of observation. In the 1970s, astronomer Vera Rubin, whose work was long overlooked partly due to the era's bias against women in science, carefully measured the rotation speeds of galaxies. According to Newton's laws of gravity and the observable mass of stars in a galaxy, stars at the outer edges of a galaxy should orbit more slowly than stars near the center, just as the outer planets of the solar system orbit the sun more slowly than the inner planets. But what Rubin found was that outer stars orbit just as fast as inner stars. The rotation curve of galaxies is flat, not declining. This can only be explained if galaxies are embedded in vast halos of invisible matter, dark matter, that provides the additional gravitational force needed to explain the observed orbital speeds. Rubin's work was confirmed by countless subsequent observations, and today dark matter is one of the most robust findings in cosmology. But what is it? We don't know. No particle consistent with dark matter has ever been detected directly, despite decades of enormously expensive and sophisticated experiments deep underground, in space, and at particle accelerators. Some of the leading candidates, weakly interacting massive particles, or WIMPs, have been searched for intensively without success. Other candidates include axions, sterile neutrinos, and more exotic possibilities like primordial black holes. Here's a thought that should make the hair on your neck stand up. The ordinary matter, the atoms, the molecules, the stars, planets, galaxies, people, everything you can see and touch and measure, makes up only about 5% of the universe. 95% of the universe is made of stuff we cannot see, cannot detect directly, and do not understand. You are standing in the middle of a room, 95% of which is made of something you cannot perceive. In fact, 95% of you. If you include the dark matter permeating your body, passing through you like a ghost, exerting unmeasurably tiny gravitational tugs on your atoms, is invisible and unknown. Dark matter passes through your body right now, every second, billions of particles streaming through you as if you weren't there, because to them, you aren't. You are as transparent to dark matter as a window is to light. Doesn't that make you feel, in a very specific and visceral way, that you are less substantial than you thought? Now let's turn to perhaps the most emotionally wrenching paradox in all of cosmology, the Fermi paradox. Because the paradoxes of time and space are not just abstract puzzles for physicists. They have consequences for us, for the human story, for the question of whether we are alone in the universe, for what it means to exist in this particular cosmic moment. The Fermi paradox is named after the physicist Enrico Fermi, who in 1950, during a lunch conversation with colleagues at Los Alamos, reportedly asked a simple question: where is everybody? Here's the setup. The universe is 13.8 billion years old. The Milky Way galaxy alone contains somewhere between 200 and 400 billion stars. Many of these stars have planets. Many of those planets are in the habitable zone, the region around a star where liquid water can exist on a planet's surface. We now know, thanks to missions like the Kepler Space Telescope, that exoplanets are extraordinarily common. The Milky Way likely contains more than 1 trillion planets. Many of them have the conditions suitable for life. Even if life arises on only a tiny fraction of those planets, the sheer number of potential life-bearing worlds is staggering. And even if only a tiny fraction of those worlds produce intelligent life, and even if only a tiny fraction of those develop technology, and even if most technological civilizations destroy themselves quickly, the numbers still suggest that the Milky Way should be teeming with intelligent civilizations. Some of them should be millions of years older than we are. A civilization that arose even 1 million years before us, a geological eye blink in cosmic time, would have had 1 million years to develop technology, to explore, to expand, to colonize, to send signals across the galaxy. We should see evidence of them everywhere. We should be receiving their signals, their probes, their artifacts. The galaxy should, by this reckoning, be full of the signs of intelligence. And yet, silence. Profound, complete, eerie silence. In more than 60 years of searching with increasingly sensitive instruments, the SETI project and its successors have scanned millions of star systems across a vast range of radio frequencies. We have found nothing. Not one confirmed signal. Not one artifact. Not one probe. The cosmos, as far as we can tell, is empty of anyone trying to reach us, or even of anyone accidentally broadcasting signals that we might overhear. This is the Fermi paradox, and it is genuinely one of the most disturbing facts about our place in the universe. There are many proposed solutions. They are called the Fermi paradox explanations, or filters, and each of them carries its own unsettling implications. One possibility is that intelligent life is genuinely, extraordinarily rare, that the emergence of complex, technological civilizations requires such a specific sequence of improbable steps that we might be the only one in the galaxy, or even in the observable universe. The biologist Ernst Mayr estimated that the evolution of intelligence on Earth required such an unlikely confluence of factors: the right kind of star, the right planetary system, the right atmospheric conditions, the right evolutionary pressures, 1,000 accidents that could so easily have gone differently, that it may be essentially unique. If this is true, then the silence of the cosmos is because we are alone. And that is, in a certain light, terrifying. An entire universe, 13.8 billion years old, 100 billion galaxies, each with hundreds of billions of stars, and we are the only minds, the only eyes, the only ears. The universe in this scenario is overwhelmingly vast, overwhelmingly old, and essentially empty of consciousness. But there is another explanation that many physicists and philosophers find even more disturbing. It's called the Great Filter. The idea, developed by economist Robin Hanson in 1998, is that somewhere along the path from primordial chemistry to galaxy-spanning civilization, there is a step, one or several, that is so improbable, so difficult to cross, that virtually no species ever crosses it. This step filters out almost all potential civilizations. The terrifying question is the Great Filter behind us or ahead of us? If it is behind us, if the incredibly unlikely step was the origin of life, or the evolution of eukaryotic cells, or the emergence of multicellular organisms, or the development of intelligence, then we are lucky survivors. We have already passed the filter. The silence of the cosmos reflects how extraordinarily rare we are, but it also means we might have a future ahead of us. But if the Great Filter is ahead of us, if it is something that all sufficiently advanced civilizations encounter and almost none survive, then the silence is not because we are rare, but because every civilization that reaches our level of development soon faces something that destroys it. Nuclear weapons, engineered pandemics, artificial intelligence, climate collapse, some unknown catastrophe that waits on the other side of technological maturity. In this scenario, the silence of the cosmos is a warning. Every civilization before us reached roughly where we are, and then went quiet. And the more evidence we find that intelligent life has arisen elsewhere, in particular, if we were to discover microbial life on Mars, or in the oceans of Europa, the more it would suggest that the emergence of life is easy, which would push the Great Filter further up the evolutionary ladder, which would mean it is closer to us, which would make the warning more urgent. This is why some scientists have argued that finding microbial life on Mars might be one of the worst things that could happen to humanity's long-term prospects. Not because of contamination or alien invasion, but because of what it would imply about the Great Filter. Let that sink in. We might be hoping, for the sake of our future, that Mars is utterly sterile. Now let's travel back in time, conceptually at least, to the very beginning of everything, because the origin of the universe is the site of the most fundamental paradox of all. The paradox of being versus nothing. Why is there something rather than nothing? This question is not simply philosophical hand-wringing. It is a genuine scientific puzzle, because the most natural state of reality, if you try to apply our best physical theories, seems to be nothing. No space, no time, no energy, no matter, no laws of physics, no anything. And yet here we are. The universe exists. Why? One possible answer, offered by quantum cosmology, is that nothing is unstable, that even a state of perfect nothingness is subject to quantum fluctuations, and that a universe can spontaneously emerge from nothing via quantum processes. Stephen Hawking and James Hartle proposed a model called the no-boundary proposal, in which the universe has no beginning in time, no edge, no singularity. Time itself becomes a fourth spatial dimension near the Big Bang, smoothing away the singularity mathematically. In their model, asking what happened before the Big Bang is like asking what is north of the North Pole. The question is grammatically valid but physically meaningless. But other physicists and philosophers push back. If the laws of quantum mechanics are what allow something to emerge from nothing, then where did the laws of quantum mechanics come from? You still need a framework, a set of rules, within which the quantum fluctuation can occur. And that framework, whatever it is something. You haven't escaped from something. You've just pushed the something back one level of abstraction. This is sometimes called the cosmological regress problem, and it has no satisfying answer in current physics. It is one of the places where science reaches its current boundary and stares into the darkness. Some physicists, like Max Tegmark, have proposed an even more radical answer: the mathematical universe hypothesis. Tegmark argues that mathematical structures are not just descriptions of reality, they are reality. Every mathematically consistent structure that can be defined exists as a physical reality somewhere. Our universe is one such mathematical structure. Other universes, with different laws of physics, different numbers of dimensions, different fundamental constants, also exist because they are also mathematical structures, and all mathematical structures exist. In this view, the answer to why is there something rather than nothing is because there is no such thing as nothing. Every possible mathematical structure, every possible universe exists. We live in this one because it's the kind of universe that can contain observers who can ask questions. This is, needless to say, an extraordinarily controversial idea, but it is held by a respectable physicist at MIT, published in peer-reviewed papers in a serious book, and it represents the logical endpoint of a certain line of reasoning about mathematical reality. Ask yourself, does it feel like reality is made of mathematics? When you look at the intricate, perfectly regular patterns of a snowflake, the orbital mechanics of planets, the waves of quantum probability, does it feel like you are looking at math brought to life, or like you are using math as a tool to describe something that is fundamentally non-mathematical? Your intuition about this might say something about which interpretation of physics you would naturally gravitate toward. Let's talk about time travel. Because no discussion of the paradoxes of time and space would be complete without confronting the possibility that has captivated human imagination for more than a century. Can you travel through time? And if you can, what happens? The good news, if you can call it that, is that time travel is not forbidden by the laws of physics. In fact, one form of it, time travel to the future, is not just possible but has already been done. It happens every time an astronaut returns from the International Space Station. They are ever so slightly in the future relative to where they would have been if they'd stayed on Earth. The effects are tiny, because the astronauts aren't going nearly fast enough or experiencing nearly enough gravity difference to produce large effects. But the principle is established and verified. More dramatic time travel to the future is theoretically possible if you travel fast enough or get close enough to a sufficiently strong gravitational field. Get into a spacecraft, accelerate to 99.999% the speed of light, travel for what feels to you like a year, then turn around and come back. Depending on your speed, you might return to find that 100 years, or 1,000 years, or more have passed on Earth. You have traveled to the future. You cannot go back. But time travel to the past? That's where the paradoxes explode. General relativity, Einstein's theory of gravity and spacetime, does not prohibit closed time-like curves, paths through spacetime that loop back on themselves, allowing an object to return to its own past. Certain solutions to Einstein's equations contain these. Kurt Gödel, the brilliant mathematician whose friendship with Einstein at Princeton was legendary, discovered in 1949 a solution to the equations of general relativity that describes a rotating universe in which closed time-like curves, time machines, in effect, exist everywhere. Gödel was deeply troubled by this, partly because he was deeply troubled by time in general, and his discovery raised the question: if general relativity permits time travel to the past, why don't we see time travelers? The most famous paradox of time travel is the grandfather paradox. The scenario goes like this. You build a time machine, travel back to before your grandfather met your grandmother, and kill your grandfather. Then you were never born. But if you were never born, you couldn't have traveled back in time and killed him. So your grandfather lived, and you were born, and you traveled back in time and killed him. But if you killed him, you weren't born. And so on, cycling in an irresolvable loop. This seems like a clear demonstration that time travel to the past is impossible. A logical reductio ad absurdum. And many physicists take this as a strong hint that closed time-like curves, whatever the mathematics allows, are not physically realizable. Stephen Hawking proposed the chronology protection conjecture, the idea that the laws of physics conspire to prevent time machines from being created, thus protecting the timeline from paradox. Though Hawking couldn't prove this from first principles, he noted that quantum effects near any incipient closed time-like curve would likely diverge, blow up to infinity, destroying the time machine before it could be used. It's as if the universe has a built-in self-defense mechanism against its own past being tampered with. But other physicists have proposed ways around the paradox. The many-worlds interpretation of quantum mechanics, for example, dissolves the grandfather paradox elegantly. When you travel back in time and kill your grandfather, you don't change your own past. You create a new branch of the universal wave function. In that new branch, your grandfather is dead, and no one born of his lineage will ever travel back to kill him. But you still exist. You came from the original branch. You are now living in a parallel timeline. Your original timeline, the one you came from, remains unchanged. In this scenario, time travel to the past doesn't change your history. It creates new histories. The paradox dissolves because the self-reference, you kill your grandfather, so you're never born, so you can't kill him, breaks down when you're allowed to branch into a new timeline. Another proposed resolution is the Novikov self-consistency principle, named after the Russian physicist Igor Novikov. This principle says, only self-consistent time travel is possible. If you go back in time and try to do something that would create a paradox, you will fail. Not because some mystical force prevents you, but because the laws of physics are self-consistent, and in a block universe, the past is already fixed. You can go back in time, but the actions you take in the past are already part of the historical record. You were always there, playing your role. The universe has already taken your visit into account. In this framework, you cannot kill your grandfather, not because you lack the ability, but because the fact of your existence proves that you didn't. Any attempts you make will fail, through bad aim, mechanical failure, a change of heart, a stumble, whatever it takes. You are not free to change the past because the past is fixed and your visit is already embedded in it. This is deeply fatalistic. It suggests that time travelers have no freedom to deviate from what has already happened. They are characters in a story whose ending is already written, playing out their scripted role without knowing it. It is perhaps the most psychologically unsettling resolution of the time travel paradox. More so than the many worlds version, because at least in many worlds you have some freedom, even if in a branching universe. Now let's explore something that bridges time travel, the nature of causality, and the structure of space-time. The question of whether the past is real. We've talked about the block universe, Einstein's view that all of time exists simultaneously. But there's an opposing view called presentism, which holds that only the present moment is real. The past has ceased to exist. The future hasn't yet come into being. There is only now. Presentism is the view most of us implicitly hold in everyday life. Of course the past is gone. Of course the future isn't here yet. What else could it be? The problem is that presentism is almost impossible to reconcile with special relativity. Here's why. Special relativity says that two observers moving relative to each other will disagree about which events are simultaneous. This is called the relativity of simultaneity. If you're standing on a train platform and I am on a passing train, and two lightning bolts strike simultaneously at the front and back of the train from your perspective, then from my perspective they do not strike simultaneously. I see the one at the front first. This is not an optical illusion. It is not because the light takes different times to reach my eyes. In the physics of special relativity, the events are genuinely simultaneous in your reference frame and genuinely not simultaneous in mine. Now, if presentism is true and only the present moment is real, then the present moment should refer to a collection of events happening now, simultaneously. But if simultaneity is observer-dependent, then different observers have different nows. My now includes events that are, for you, in the past or the future. So whose present is real? If presentism is true, there should be a privileged observer, a correct reference frame whose now corresponds to what is really present. But special relativity says there is no privileged reference frame. All are equally valid. Therefore, presentism and special relativity are almost certainly incompatible. If special relativity is correct, and it is one of the most well-tested theories in all of science, then presentism is wrong. The past is real. The future is real. The block universe is real. But if the block universe is real, and all moments exist simultaneously, then why does it feel like time is passing? Why does consciousness seem to move through time like a spotlight through darkness, illuminating now, while leaving the past in shadow and the future unlit? This is the arrow of time problem, and it is intimately connected to one of the most fundamental laws of physics, the second law of thermodynamics. The second law of thermodynamics states that the total entropy, a measure of disorder or randomness, of a closed system can never decrease over time. It can stay the same in reversible processes or increase in irreversible processes. Entropy is always marching in one direction, from order to disorder, from low to high, from concentrated to diffuse. This is why ice melts in warm water, but warm water never spontaneously freezes into ice. This is why you can scramble an egg but never unscramble it. This is why the cream swirls into your coffee and disperses but never spontaneously reassembles into a floating blob. This is why living organisms age and die, but corpses do not spontaneously come back to life. Entropy increases. Disorder wins. Always. And here is the astonishing thing. The second law of thermodynamics appears to be the only law of physics that distinguishes the past from the future. All other fundamental laws, Newton's laws, Maxwell's equations, quantum mechanics, general relativity, are symmetric in time. Run a physical process forward and backward. The mathematics looks exactly the same. A ball thrown up into the air follows the same equations backward as forward. Two billiard balls colliding follow the same equations backward as forward. At the microscopic level, the laws of physics make no distinction between past and future. But the second law does. Entropy increases toward the future, decrease toward the past. The arrow of time, the direction in which time seems to flow, is given to us by entropy. We remember the past and not the future because in the past, entropy was lower. Causes precede effects because the universe began in an extraordinarily low entropy state, the Big Bang, and has been increasing in entropy ever since. But this raises a profound question. Why did the universe begin in such a low entropy state? The Big Bang was an incredibly dense, incredibly hot, incredibly ordered state. Ordered not in the sense of being geometrically regular, but in the thermodynamic sense of having all the energy concentrated rather than dispersed. The subsequent history of the universe is one of entropy increasing, energy spreading out, structures emerging and then dissolving, complexity growing at the expense of even greater disorder elsewhere. The low entropy beginning of the universe is, in the words of physicist Roger Penrose, extraordinarily improbable. Penrose has calculated that the probability of the universe having begun in such a low entropy state by chance is something like 1 in 10 to the power of 10 to the power of 123. This is not just an astronomically large number. It is a number so large that writing it out in full would require more digits than there are atoms in the observable universe. Many times over, the specialness of the initial state of the universe is, in statistical terms, almost infinitely improbable. Why was the initial state of the universe so special? This is perhaps the deepest question in all of cosmology, and it connects to the deepest question in all of physics. Why are the laws of nature the way they are? Because the laws of nature, the fundamental constants, the number of dimensions of space and time, the strength of gravity, the masses of particles, the speed of light, did not have to be the way they are. Change any of them slightly, and you get a universe that is profoundly different, and almost certainly dead. Lifeless. Without stars, without planets, without chemistry, without the possibility of any kind of complexity. This observation, that the constants of nature appear to be fine-tuned for the existence of life, is called the fine-tuning problem, and it is one of the most contentious issues in contemporary physics and cosmology. Consider the cosmological constant, the value associated with dark energy. For the universe to have expanded slowly enough to allow galaxies and stars and planets to form, rather than expanding in a single burst of energy with nothing condensing into structures, the cosmological constant must be extraordinarily small, but not zero. If it were even slightly larger, the universe would have expanded too fast for matter to clump together. No galaxies, no stars, no planets, no life. If it were negative and of sufficient magnitude, the universe would have collapsed back on itself before any complexity could arise. The cosmological constant must fall in an extraordinarily narrow range for life to be possible, and yet it does. The same is true of the strength of the strong nuclear force, which holds atomic nuclei together. If it were even slightly weaker, protons and neutrons would not bind together, and there would be no atoms heavier than hydrogen. No carbon, no oxygen, no chemistry, no life. If it were slightly stronger, all hydrogen would fuse rapidly into helium during the Big Bang, leaving no hydrogen for stars to burn or for water to form. No life. The fine-tuning of these constants is so precise, and the probability of getting them right by chance is so astronomical that it demands an explanation. And there are essentially three classes of explanation. The first is theism. The constants are fine-tuned because the universe was designed by an intelligence that intended for life to exist. This is not a scientific hypothesis. It doesn't make testable predictions, but it is held by many thoughtful people as a reasonable metaphysical response to the fine-tuning evidence. The second is the anthropic principle. We observe the constants to have the values they do because if they didn't, we wouldn't be here to observe them. This is logically valid but doesn't really explain the fine-tuning. It just says that we're in a fine-tuned universe because we couldn't be in a non-fine-tuned one. The explanation of why there is a fine-tuned universe for us to be in is not addressed. The third is the multiverse. There are an enormous number, perhaps infinitely many, universes, each with different values of the fundamental constants. We necessarily find ourselves in one that has life-permitting values, because we couldn't exist in one that doesn't. The multiverse makes the fine-tuning unsurprising. If you have enough universes with random constants, some will be life-permitting, and those are the ones that will have observers puzzling over why their constants are so special. The multiverse is not a single theory but a family of theories, and some versions of it have more scientific support than others. The inflationary multiverse, based on the theory of cosmic inflation, which holds that the early universe underwent a period of exponential expansion, naturally produces vast numbers of separate bubble universes, each potentially with different physical constants. The string theory landscape, the enormous space of possible vacuum states in string theory, estimated to contain something like 10 to the power of 500 different possible universes, similarly suggests a vast multitude of universes with varying laws. But the multiverse is also deeply controversial, partly because it seems untestable in principle. How could we ever observe a universe other than our own? And partly because some physicists feel it is scientifically irresponsible to invoke an unobservable infinity of universes to explain the properties of the one we can see. Stephen Hawking, in his final book, Brief Answers to the Big Questions, published posthumously in 2018, stated his belief that the top-down version of the no-boundary proposal might tame the multiverse, constraining the range of possible universes to those similar to our own. But this remains deeply speculative. Here is something to consider. Even if the multiverse exists, even if there are infinite universes, the question, why is there something rather than nothing, remains. Because an infinite multiverse is still something. The whole framework of mathematics, quantum mechanics, the laws that allow quantum fluctuations to produce universes, all of this is something. The question hasn't been answered. It has been expanded. Perhaps, why is there something rather than nothing? Is the one question the universe, by its very nature, cannot answer from within itself. It is the philosophical equivalent of a closed time-like curve, a question that loops back on itself, that contains within it the very framework that would be needed to answer it. A paradox, complete and irreducible. Now, let's descend into something even more personal and potentially destabilizing. Because all of these paradoxes, Zeno's tortoise, the block universe, the measurement problem, the Fermi paradox, the fine-tuning problem, have a common thread. They are not just puzzles about the external universe. They are puzzles about the relationship between the universe and the observers within it, between the cosmos and consciousness. And this brings us to what may be the deepest paradox of all, the hard problem of consciousness. The hard problem, as formulated by philosopher David Chalmers in 1995, is this: why does physical processing in the brain give rise to subjective experience? Why is there something it is like to be you? Think about it. You have a brain. That brain is made of neurons, biological cells that process electrochemical signals. We can trace the pathways by which light hits your retina, is converted to electrical signals, is transmitted to your visual cortex, is processed by various areas of the brain, and produces a behavioral response. You reach out and pick up the object you're looking at, for example. This is the easy problem of consciousness. Not easy to solve, but at least the kind of problem we know how to approach. We can, in principle, give a complete functional account of what the brain does without ever mentioning subjective experience. But the hard problem is different. Alongside all this physical processing, there is your experience of redness, the felt quality of what it is like to see red. Not just the processing of wavelengths of light around 700 nanometers, but the experience, the qualia, the what it is like. This is not captured by any functional or physical description, however detailed. You can know everything about the physics and chemistry of a human brain and still, Chalmers argues, have no idea why there is any experience at all, rather than just mindless processing in the dark. And here is where it connects to the paradoxes of time and space. Because if consciousness is required for the collapse of quantum wave functions, as some interpretations of quantum mechanics suggest, then consciousness is not a byproduct of the physical universe. It is, in some sense, a necessary ingredient of reality itself. Some physicists, most notably Eugene Wigner and, more recently, Andre Linde, have proposed that consciousness plays a fundamental role in the structure of reality. Not in a mystical sense, but in a specifically physical sense connected to quantum measurement. And if the block universe is real, if all of space-time exists simultaneously, then what is consciousness? It is not moving through time in the block universe. It is a static pattern in the four-dimensional block. But then why does it feel like time is passing? Why does it feel like you are in the present? The philosopher Barry Dainton has proposed that consciousness exists as a kind of thread through the block universe, stream of consciousness that is a real structural feature of spacetime, not an illusion. But this doesn't resolve the mystery of why the thread seems to move. Other philosophers, like Julian Barber, argue that each slice of time, each moment in the block universe, contains its own memories, its own apparent past, but that there is no actual movement between slices. Each moment simply contains the experience of being a moment with a past. There is no you that moves from one moment to the next. There are just countless static moments, each of which thinks it is moving through time, because each contains the memory of previous moments. This is perhaps the most vertiginous idea on this entire journey, because it means that the self, the continuous, flowing, experiencing I, that you identify as yourself may not exist in the way you think it does. It may be a kind of narrative constructed after the fact by a brain that is exquisitely good at creating the illusion of continuity. Each moment of consciousness is its own self-contained event, containing a memory of the past and an anticipation of the future, but not actually connected to any previous moment except through the chain of physical causation. The Buddhist philosophical tradition arrived at a similar conclusion more than 2,000 years ago. The self is not a real, enduring entity but a constantly changing process, a stream of experiences with no permanent, fixed essence. What physics calls the block universe, and what Buddhism calls anatta, non-self, may be pointing at the same truth from different directions. Ask yourself, if the self that you think of as you is a narrative construction, a story your brain tells about a continuous entity that doesn't really exist as a permanent thing, does that change how you relate to your past self? To your future self? To other people? Now let's turn to another class of paradox that emerges from the intersection of infinity and cosmology. Because the universe may be infinite, and if it is, the consequences are literally mind-shattering. Modern cosmology gives a strong reason to believe that the observable universe, the region of the universe from which light has had time to reach us since the Big Bang, is not the whole universe. The universe extends beyond what we can see, perhaps infinitely. The observable universe is a sphere about 93 billion light-years in diameter, centered on Earth. It is larger than the age of the universe in light-years because of the expansion of space. But beyond that sphere, space continues, and may continue forever. If the universe is truly infinite in extent, and if the laws of physics are the same everywhere, and if matter is distributed roughly uniformly throughout, which our observations of the observable universe suggest, then something extraordinary follows. An infinite universe, with matter distributed uniformly, will contain an infinite number of regions the size of our observable universe. And with an infinite number of regions, each containing a finite number of possible configurations of matter, the laws of probability guarantee that every possible configuration of matter will repeat. Not just once, but infinitely many times. This means that somewhere in an infinite universe, there is an exact copy of you, atom for atom, thought for thought. Somewhere there is a region of space identical to our observable universe in every detail. And beyond that, there are regions that differ only slightly from ours. Somewhere there is a version of you who made every slightly different decision. Somewhere there is a version of Earth where history unfolded differently in every possible way. In an infinite universe, every possible arrangement of matter that is physically possible, every possible history, every possible civilization, every possible person, exists, infinitely many times. This is the cosmological Boltzmann brain problem, named after Ludwig Boltzmann, the 19th century physicist who pioneered statistical mechanics. In a universe of infinite size and infinite time, statistical fluctuations can produce anything, including, temporarily, a fully formed human brain complete with memories of a past that never happened, floating in empty space and experiencing a moment of consciousness before dissolving back into chaos. These Boltzmann brains should, in principle, be vastly more common than real brains that arose through billions of years of evolution, because it is statistically more likely for a random fluctuation to produce a single brain than to produce an entire universe hospitable to life. So here's a question that should chill you. How do you know you are not a Boltzmann brain? How do you know that your memories of a past, your experience of a physical body, your perception of a world around you are not the product of a random quantum fluctuation in an otherwise empty cosmos, about to dissolve? You can't. Your evidence for the reality of the external world is the very memories and perceptions that, in this scenario, were fabricated by the fluctuation that created you. This is the deepest form of the philosophical problem of solipsism, but given a physical, cosmological form. And it is taken seriously enough that cosmologists have proposed it as a problem for any theory that predicts an infinite universe or infinite time. Because such a theory, if it produces an infinite number of Boltzmann brains, fails to explain why we experience a coherent universe rather than a random bubble of experience. Some cosmologists, like Sean Carroll at Caltech, argue that Boltzmann brains are only a problem if you misapply the mathematical framework of statistical mechanics to situations for which it wasn't designed. In particular, if you naively apply it to an infinite universe over infinite time. Others take the problem seriously and use it as a constraint on cosmological models. But the image lingers, doesn't it? The image of a mind, perhaps your mind, as a temporary island of coherence in an ocean of chaos, convinced it has a past and a future, surrounded by a world that it believes is real, with no way of ever knowing for certain whether it is. Let us take a breath. Let us return to something more immediate, more visceral, more human. Let's talk about the event horizon of a black hole again, but this time from a different angle. One that connects to perhaps the most dramatically counterintuitive prediction of modern physics, one that physicists themselves found deeply troubling when it was first proposed. This is the story of the firewall paradox, and it involves a conflict so deep that it has been called the most dangerous idea in physics. It starts with a principle called complementarity, developed by Leonard Susskind and Gerard T. Hooft in the 1990s as a way to resolve the black hole information paradox. The idea of black hole complementarity says that two observers, one falling into a black hole and one watching from the outside, will have completely different but equally valid descriptions of what happens at the event horizon, and crucially, neither observer can ever compare notes, because the infalling observer can never communicate with the outside once they've crossed the horizon. So there's no contradiction, even if their descriptions are wildly different. For the infalling observer, nothing special happens at the event horizon. They cross it smoothly, unaware of the moment of crossing, and only realize they're inside when they can no longer escape, if they can even realize it, because the tidal forces inside a large black hole near the horizon are very gentle. For the outside observer, the infalling person is heated up and destroyed at the horizon by Hawking radiation, and their information is encoded in that radiation and eventually recovered. Both descriptions are true for their respective observers. Neither can be falsified by comparing them, because quantum mechanics prevents the necessary communication. Complementarity was controversial but tolerated. Then, in 2012, Ahmed Almhiri, Donald Merolf, Joseph Polchinski, and James Sully, in a paper now known as AMPS after their initials, dropped a bomb on the physics world. They showed that black hole complementarity cannot work. The mathematics, when pushed carefully, leads to an irresolvable contradiction, and the only way out seems to be the existence of a wall of fire, a firewall, at the event horizon of an old black hole, one that has been evaporating long enough to have lost more than half its information. This firewall would be a region of incredibly high-energy radiation that would instantly incinerate anyone falling through the horizon. So the infalling observer would not experience a smooth crossing. They would be burned to nothing. The principle of equivalence, Einstein's sacred principle that says you can't distinguish being in free fall from being in deep space, which is the very foundation of general relativity, would be violated. So we have a choice. Violate the principle of equivalence, which is the cornerstone of general relativity, or violate the unitarity of quantum mechanics, which says information cannot be destroyed. These are both foundational principles of the two great pillars of modern physics, and they appear, in this context, to be genuinely incompatible. This is the firewall paradox, and it has not been resolved. As of the most recent literature, it remains one of the most hotly debated open problems in theoretical physics. Some physicists think the firewall is real. Some think there's a loophole in the argument. Some think it points to a fundamental incompatibility between quantum mechanics and general relativity that can only be resolved by a new theory, a theory of quantum gravity that we don't yet have. The search for a theory of quantum gravity is perhaps the central quest of theoretical physics today. We have two extraordinarily successful theories: quantum mechanics, which describes the behavior of matter and energy at the smallest scales with breathtaking precision, and general relativity, which describes gravity and the structure of spacetime at large scales with equal precision. Both theories have been tested exhaustively and have passed every test, but they are mathematically incompatible. You cannot simply combine them into a single equation. When you try, You get infinities, nonsensical results that signal a breakdown of the theoretical framework. The leading candidate for a theory of quantum gravity is string theory, which replaces point particles with one-dimensional strings of energy whose different vibrational modes correspond to different particles. String theory naturally incorporates gravity and does not produce the infinities that plague attempts to combine quantum mechanics and general relativity directly. But it requires the existence of extra spatial dimensions, typically 6 or 7 beyond the 3 we experience, which are presumably compactified, curled up into shapes so small that we cannot perceive them. String theory also predicts an enormous landscape of possible universes, the 10 to the power of 500 possible vacuum states mentioned earlier, which some take as support for the multiverse and others take as a sign that the theory makes no specific predictions and therefore isn't real science. Another candidate is loop quantum gravity, which takes a different approach. Rather than trying to describe everything in terms of vibrating strings, it attempts to quantize spacetime itself, to describe space and time in terms of discrete, quantized units called spin networks and spin foams. In loop quantum gravity, space is not a continuous fabric but a network of quantum nodes and links, and time is not a smooth flow but a series of discrete transitions between states of this network. If loop quantum gravity is correct, the Planck scale granularity of space and time that we discussed at the beginning is not just a hint or a guess, it is a fundamental feature of the theory. Space-time is literally quantized, like the energy levels of an atom. And if space-time is quantized, then the singularities of general relativity, the point of infinite density at the center of black holes, the initial singularity of the Big Bang, are resolved. A singularity in general relativity represents a breakdown of the theory, a point where space-time curvature becomes infinite and the equations break down. In loop quantum gravity, the quantization of space-time prevents the curvature from reaching infinity, so the singularity is replaced by a finite density region where quantum gravity effects dominate. What we call the Big Bang is, in some loop quantum gravity models, actually a big bounce, a contraction of a previous universe that hit the Planck density limit and began expanding again. Our universe is, in this view, the child of a previous universe that collapsed. The idea of a bouncing cosmology, an infinite cycle of expansion, contraction, and rebirth, has a long history, both in Eastern philosophical traditions and in Western cosmology. It is deeply appealing in its suggestion that existence has no beginning and no end, that the universe is eternally cycling through states, that the question, what came before the Big Bang, has an answer, a previous universe. But bouncing cosmologies face their own version of the entropy problem. The second law of thermodynamics says entropy always increases. So if the universe contracts and then bounces, the entropy of the new expanding phase should be even higher than at the end of the contracting phase. Over many bounces, entropy accumulates. If you run the series backward, you must eventually reach a universe with essentially zero entropy, the most perfectly ordered, most improbable state imaginable. Which brings you back to the question, why was the initial state of the universe, the first universe in the series, if there was one, so perfectly ordered? This seems to be an inescapable problem. Every cosmological model that tries to avoid a beginning eventually has to explain the extraordinary low-entropy initial state of whatever it begins with. The problem doesn't go away with bouncing universes, eternal inflation, or anything else. It seems to be a fundamental feature of the question itself, which perhaps suggests that the universe did have a beginning, a moment of creation that is genuinely the first moment, with no before, just as Hawking suggested. But that only relocates the mystery. Why that beginning, out of all possible beginnings? Let's talk about something that brings all of these cosmic abstractions crashing back into your personal, lived experience with tremendous force. Let's talk about the nature of the moment, the present, the now. We've already established that physics suggests the present has no thickness, that it is an infinitely thin boundary between past and future. But let's think about what the now feels like from the inside, because the subjective experience of the present is one of the strangest facts about consciousness. When you experience the present moment, you are not actually experiencing what is happening right now. You are experiencing the past, your very recent past, by about a third of a second or so. This is because your brain takes time to process sensory information. The light hitting your eyes, the sound waves hitting your ears, the pressure on your skin. All of these signals have to travel to your brain, be processed, integrated, and then presented to your conscious experience as a unified now. By the time you consciously experience now, the moment has already passed. In 2002, neuroscientists Haggard and Eimer, building on earlier work by Benjamin Libet, conducted experiments showing that the brain's decision to make a voluntary movement, raising a finger, say, occurs about 300 to 500 milliseconds before the person becomes consciously aware of the decision. The brain initiates the action before consciousness knows about it. If this is correct, then you, your conscious self, don't actually decide to move your finger. Your brain decides, and then informs consciousness after the fact, creating the illusion of a conscious decision. Libet himself, to his credit, acknowledged the disturbing implications for free will. His famous suggestion was that although the brain initiates action unconsciously, consciousness might retain a veto, the ability to cancel the initiated action. But even this veto, subsequent research suggests, may itself be neurally prepared before consciousness is aware of it. The question this raises about free will is profound and has not been resolved. If every decision your brain makes is neurally determined before you're conscious of it, if your consciousness is receiving a report of what has already been decided rather than making the decision, then in what sense are you making choices? In what sense is you, as a conscious entity, in control of your behavior? Some philosophers argue that this is not the right way to think about free will, that free will is compatible with determinism, and that what matters is not whether your decisions are neurally prepared before consciousness, but whether they arise from your own reasoning and values. This is called compatibilist free will. Others argue that the Libet results are deeply troubling and that our sense of being the author of our actions is a fundamental illusion. And here the paradoxes of time and space meet the paradox of selfhood in the most intimate possible way. Because if the block universe is real, if all moments already exist, then every decision you will ever make already exists in the four-dimensional space-time block. The future is already there, fixed and real. There is nothing to decide. The sensation of deciding is a feature of consciousness navigating through the block universe, the experience of not yet knowing what is already determined. In this view, free will is not an illusion in the sense of being meaningless. The deliberation is real, the values driving the decision are real, the connection between reason and action is real. But the openness of the future, the genuine possibility of things being otherwise, is an illusion. The future is as fixed as the past. You just can't see it yet. Here is a question that might keep you up at night. If the future is fixed and already real in the block universe, would you want to know it? If you could look forward in the block and see every moment of your life, every joy, every loss, every mundane Tuesday morning, would that knowledge make your life richer, or would it drain it of all meaning? Perhaps the sensation of time passing, of the future being genuinely open, is the condition for life as we experience it. Perhaps consciousness, whatever it ultimately is, requires the experience of uncertainty, of choosing, of not knowing what comes next. Perhaps the illusion of time's flow and free will is not a mistake, but a necessary feature of what it means to be a mind embedded in a physical world. Now let's visit one more class of paradox, one that has particular resonance in the age of quantum computers and artificial intelligence, before we turn toward our conclusion. It is the paradox of computation and mathematics. Kurt Gödel, whom we mentioned earlier as having discovered time travel solutions in general relativity, was also responsible for one of the most earth-shaking results in the history of mathematics. The incompleteness theorems, proved in 1931. Gödel's first incompleteness theorem says, in any consistent formal system that is powerful enough to describe the arithmetic of natural numbers, there exist true statements that cannot be proved within the system. In other words, mathematics contains truths that mathematics cannot prove. There is always something beyond the reach of any system of rules, always a true statement that cannot be demonstrated using the tools of that system. Gödel's second incompleteness theorem goes even further. No consistent formal system can prove its own consistency. You cannot use mathematics to prove that mathematics is free from contradiction. There is no self-contained foundation for mathematics that can demonstrate its own reliability. These results were devastating to the project of David Hilbert and others, who had hoped to build all of mathematics on a complete, consistent set of axioms. Gödel showed that this project was impossible. Mathematics is, at its core, irreducibly open. It contains an infinite horizon of truth that no finite set of axioms can exhaust. The implications spread well beyond mathematics. Alan Turing, building on Gödel's work in 1936, proved the halting problem, that there is no general algorithm that can determine, for an arbitrary computer program, whether it will eventually halt or run forever. There are problems that are mathematically well-defined but algorithmically undecidable. Computers, or more precisely, the mathematical models of computation, have fundamental limitations that are not engineering problems but mathematical impossibilities. Here is where it connects to the paradoxes of time and space in a startling way. Roger Penrose, in his books The Emperor's New Mind, 1989, and Shadows of the Mind, 1994, argues that human mathematical insight, the ability to recognize mathematical truth that cannot be derived by any formal algorithm, suggests that human consciousness is not merely a computational process. It is something more, and that something more might be linked to quantum processes in the brain. Specifically, to quantum effects in structures within neurons called microtubules, as proposed in collaboration with anesthesiologist Stuart Hameroff. This is a highly controversial hypothesis. The majority of neuroscientists are skeptical that quantum effects in warm, wet biological tissue could survive long enough to play a role in cognition. But Penrose's argument from Gödel's theorem, that human mathematical understanding transcends computation, has been debated intensively and has not been straightforwardly refuted. If Penrose is right, then the mind is not just a complex computer. It is something that, in some sense, reaches beyond the formal systems that define computation. And if the mind reaches beyond formal systems, then perhaps consciousness is not just a product of the physical universe describable by our current mathematics, but something that participates in a deeper level of reality, the level at which mathematical truths exist prior to any formal system, at which something is true in a way that transcends provability. This brings us back, in a full circle, to the question we started with: what is reality? Not just what is it made of, particles, fields, strings, whatever, but what is it fundamentally? Is it mathematical? Is it computational? Is it mental? Is it something for which we don't yet have a word, because our current conceptual framework is as inadequate to the true nature of reality as a medieval peasant's framework was to quantum mechanics? We don't know. And that "we don't know" is not a confession of failure. It is a description of where we stand at this moment in the history of human understanding. At the edge of the known, looking into the darkness, with the wind in our faces and our instruments in our hands and our minds straining to grasp something that may forever remain just beyond our reach. Let's now turn to one of the most spectacular and recently confirmed predictions of general relativity. One that connects the abstract mathematics of curved spacetime to a direct, visceral experience of the universe's deepest workings. Let's talk about gravitational waves. Einstein's general relativity predicts that when massive objects accelerate, especially when two massive objects orbit each other and spiral together, they should disturb the fabric of spacetime, sending ripples outward through the cosmos at the speed of light. These ripples are gravitational waves, not waves of light or sound or matter, but waves of spacetime itself, stretching and compressing space as they pass. Einstein himself was not sure gravitational waves were real. He went back and forth on the issue, at one point submitting a paper to Physical Review claiming they didn't exist. It was rejected. Eventually, the theoretical picture became clear. Gravitational waves should exist. But detecting them requires measuring changes in distance so incredibly tiny that Einstein doubted it could ever be done in practice. The fractional change in distance caused by a gravitational wave passing through the Earth from a typical astrophysical event is on the order of 1 part in 10 to the 21st. To detect this, you need to measure the distance between two mirrors with a precision 1,000 times smaller than a proton. It seemed hopeless. Einstein died in 1955 without ever seeing evidence for gravitational waves. Then, on September 14, 2015, at 5:51 a.m. Eastern Daylight Time, the LIGO detectors, two enormous laser interferometers, one in Hanford, Washington, and one in Livingston, Louisiana, registered a signal that had traveled 1.3 billion light-years through the universe to reach us. 1.3 billion years ago, two black holes, each roughly 30 times the mass of the Sun, spiraled together and merged in a catastrophic collision that released more energy in its final fraction of a second than all the stars in the observable universe combined. The space-time ripple from that event, diluted across 1.3 billion years of cosmic expansion, arrived at our planet and stretched and compressed the 4-kilometer arms of the LIGO detectors by a distance 20 times smaller than a proton. And LIGO felt it. The signal matched the predictions of General Relativity with extraordinary precision. It was the direct detection of gravitational waves, the first direct proof of one of General Relativity's most exotic predictions. It was the first time in human history that we heard the universe, not through electromagnetic radiation, which has been our window on the cosmos for all of history, but through gravitational waves, ripples in space-time itself. Physicists described it as opening a new sense organ with which to perceive the universe. Since then, LIGO and its European counterpart, Virgo, have detected dozens of gravitational wave events. Mergers of black holes, mergers of neutron stars, combinations. Each one is a direct record of an event from the deep past, a cosmic drama played out in the darkness of space that we can now, for the first time, listen to. The merger of two neutron stars, the event called GW 170817, detected in August 2017, was simultaneously observed in electromagnetic radiation across the entire spectrum, from gamma rays to radio waves, by telescopes around the world. This was the dawn of multi-messenger astronomy, the ability to study cosmic events through both gravitational waves and light simultaneously. The event confirmed that short gamma-ray bursts are caused by neutron star mergers and provided compelling evidence that heavy elements, gold, platinum, uranium, are forged in the intense heat and pressure of neutron star collisions. The gold in your jewelry, the platinum in your catalytic converter, the uranium in nuclear power plants. All of it was born in the death spiral of neutron stars, and a gravitational wave detector proved it. You are wearing the aftermath of ancient stellar catastrophes. You are made of the debris of collapsing stars. And now, for the first time, we can hear the event as it happens. Or rather, as it happened, across distances measured in billions of light years and billions of years ago. This brings us to a beautiful and poignant paradox. The speed of light, which is the maximum speed of information in the universe, means that everything we observe is a view of the past. The sun we see is 8 minutes old, the sun as it was 8 minutes ago. The nearest star, Proxima Centauri, appears as it was 4.2 years ago. The Andromeda Galaxy, visible to the naked eye as a faint smear, shows us its state 2.5 million years ago. The most distant galaxies visible to powerful telescopes show us the state of the universe 10, 11, 12, 13 billion years ago, when the universe was young and galaxies were being assembled for the first time. We are looking at history. Our entire view of the universe is a view into the past, and the further we look, the deeper into the past we see. The observable universe is not a snapshot of the universe as it is now. It is a layered archaeological record, each layer from a different era, each more ancient than the last. We are temporal archaeologists, reading the universe's past from the light that has been traveling toward us since before the Earth existed. And now, with gravitational waves, we can look even further. Because gravitational waves, unlike light, were not blocked by the cosmic microwave background, the wall of hot plasma that filled the universe for its first 380,000 years, making the universe opaque to light. Before that time, no photons could travel freely. Light cannot show us anything from those first 380,000 years. But gravitational waves from that era, if any were produced, could reach us. In principle, a gravitational wave observatory sensitive enough could detect the gravitational waves produced in the first fractions of a second after the Big Bang, a literal recording of the birth of the universe. Plans for just such an observatory, the Laser Interferometer Space Antenna, or LISA, have been approved by the European Space Agency and are planned for launch in the 2030s. LISA will be a gravitational wave detector not on Earth but in space. 3 spacecraft separated by millions of kilometers, connected by laser beams, floating in a triangle formation, capable of detecting gravitational waves far below the frequency range accessible to LIGO. LISA will hear the gravitational waves produced by merging supermassive black holes, the titans at the centers of galaxies, and may even detect primordial gravitational waves from the Big Bang itself. Imagine this. Within the next few decades, we may be able to listen to the sound of the universe being born. Not a metaphor. A direct physical measurement of gravitational waves from the first moments of the Big Bang. This is not science fiction. This is the trajectory of real science, funded by real agencies, designed by real engineers. And yet even this extraordinary capability will not answer the deepest questions. It will not tell us why the universe was born. It will not tell us why the laws of physics have the form they have. It will not tell us whether there are other universes, what preceded the Big Bang, if anything, why entropy began so low, or what dark energy is. Those questions remain, and may remain for centuries, or forever. There is one more paradox I want to explore before we approach the end of this journey. A paradox that is geometrically beautiful, philosophically vertiginous, and personally affecting in a way that few ideas in physics manage to be. It is called the Boltzmann's brains universe cousin and is related to the question of the past's reality, and it is connected to the strangest feature of the quantum world, quantum entanglement. Quantum entanglement is a phenomenon in which two particles, once they have interacted, become correlated in such a way that measuring one instantly affects the other, no matter how far apart they are. Einstein famously called it spooky action at a distance, and was deeply uncomfortable with it. He co-authored a paper in 1935, known as the EPR paper, for Einstein, Podolsky, and Rosen, arguing that quantum mechanics must be incomplete, that there must be hidden variables that determine the outcomes of quantum measurements in advance, so that the apparent instant correlation between distant particles is not a genuine non-local influence, but merely a revelation of pre-existing information. John Bell, an Irish physicist at CERN, proved in 1964 that the predictions of any hidden variable theory must differ from the predictions of quantum mechanics in specific, measurable ways. His result, Bell's theorem, is one of the most important theoretical results in the history of physics. It converts a philosophical argument about the interpretation of quantum mechanics into a practical experimental question. In 1982, the French physicist Alain Aspect performed the first decisive test of Bell's theorem, and the results were unambiguous. Quantum mechanics is right and hidden variable theories are wrong. The correlations between entangled particles are genuinely non-local. They are stronger than any pre-existing, locally determined hidden variable theory could produce. Subsequent experiments, including loophole-free tests in 2015 by groups in Delft, Vienna, and Boulder, have confirmed this beyond any reasonable doubt. Quantum entanglement is real. Entangled particles are correlated in a way that no classical, local, realistic model can explain. What this means is that the universe is not locally realistic. Either particles don't have definite properties before being measured, they aren't real in the conventional sense. Or information travels between entangled particles faster than light, it isn't local. Or both. Most physicists go with the first option. Particles don't have definite properties before measurement. Reality, at the quantum level, is not a collection of pre-existing facts waiting to be discovered. It is a collection of potential facts that are actualized by measurement. The beautiful and disturbing thing about entanglement is that it persists over any distance. In principle, two entangled particles could be on opposite sides of the observable universe, and measuring one would instantly affect the result of measuring the other. The correlation is instantaneous. But, and this is crucial, it cannot be used to send information faster than light, because the result of each measurement is random, and you can only discover the correlation by comparing notes, which requires sending a signal through ordinary channels, which is limited to the speed of light. Entanglement is a real, non-local, faster-than-light correlation that nonetheless cannot be used for faster-than-light communication. This is a paradox in the aesthetic sense, a beautiful, tantalizing ability to connect across space that is frustratingly useless for the very thing you'd most want to use it for. But entanglement has uses. Quantum cryptography, quantum computing, and quantum teleportation, which teleports the quantum state of a particle, not matter, and which has been experimentally demonstrated across increasing distances. Most recently over 1,000 kilometers via China's Mishia satellite, are all based on entanglement. And they are genuinely transforming technology in ways that will reshape the relationship between information, security, and computation in the coming decades. In fact, quantum computers, machines that exploit superposition and entanglement to perform certain calculations exponentially faster than classical computers, represent a direct technological implementation of the most counterintuitive features of quantum mechanics. A quantum computer doesn't just try all possible solutions one at a time. In a sense, it explores a quantum superposition of all possible solutions simultaneously, and through careful manipulation of interference, the way quantum amplitudes add and cancel, it coaxes the right answer to the surface. IBM, Google, IonQ, and dozens of other companies and research groups are racing to build increasingly powerful quantum computers. In 2019, Google announced that its quantum computer had performed a specific calculation in 200 seconds that would take the world's most powerful classical supercomputer approximately 10,000 years. This claim, quantum supremacy, was contested by IBM, but it marked a symbolic milestone. Quantum computers are no longer theoretical. They are real, they are being built, and their capabilities are increasing rapidly. What a fully powerful quantum computer could do, if and when one is built, includes breaking most of the current encryption that protects financial transactions, government communications, and personal data. It could simulate quantum chemistry, transforming drug discovery and material science. It could model quantum systems of interest for fundamental physics, helping to probe the interiors of black holes and the structure of quantum gravity through controlled tabletop experiments. The paradoxes of time and space are not just philosophical curiosities. They are driving the most cutting-edge technology of the 21st century. They are changing the world. And now, as we begin to turn toward the close of this journey, let's talk about one of the most emotionally resonant of all the paradoxes of time: the paradox of cosmic scales and human significance. We have traveled through Zeno's infinite divisions, through Einstein's curved spacetime, through Hawking's evaporating black holes, through the many worlds of quantum mechanics, through the dark and silent cosmos of the Fermi paradox, through the granular floor of spacetime at the Planck scale, through the infinite repetitions of the multiverse, through the gravitational wave echoes of ancient collisions. We have stared into the face of profound uncertainty and asked hard questions about the nature of reality, consciousness, time, and existence. And now here is the last and perhaps most affecting paradox of all. You exist. Against all the odds, in a universe that is 13.8 billion years old and 93 billion light-years in radius, in which the vast majority of space and time is empty, cold, and hostile to life, in which the emergence of complexity required a set of physical constants calibrated to a precision that beggars imagination, in which the emergence of life required billions of years of evolution and an astronomical number of lucky accidents, in which the emergence of consciousness required still more improbable steps that we do not yet understand. In all of this, you exist. You exist right now, at this specific moment in cosmic history. Not in the young universe, when the first stars were lighting up in the darkness. Not in the far future, when the last stars will be dying and the universe will be settling into its final, cold equilibrium. But now, this moment, a moment rich enough with starlight and complexity and life and thought to support a being capable of asking these questions. The physicist and author Carl Sagan said, "We are a way for the cosmos to know itself." And this is not mere poetry. It is, in a very real sense, the truth. You are made of atoms forged in stellar interiors and scattered by stellar explosions. You are made of the same hydrogen that filled the early universe, the same carbon that was cooked in the cores of dying stars, the same iron that was spewed into space by a supernova more than 5 billion years ago. You are a temporary, exquisitely organized pattern of cosmic matter that has, through the incomprehensible complexity of life and evolution, become capable of wondering about the nature of the cosmos from which it arose. The universe is aware of itself through you. Your curiosity is the universe's curiosity. Your wonder is the universe's wonder. Your confusion in the face of these paradoxes is the universe confronting the limits of its own self-knowledge. And consider this. The paradoxes we have explored, the ones that feel most disturbing, most destabilizing, are not signs that the universe is broken. They are signs that reality is richer, stranger, and more profound than any model we have yet devised. Every paradox is a door. Every apparent contradiction is a clue. Every place where our understanding breaks down is a place where deeper understanding is waiting to be found. Zeno's paradoxes led to calculus. The paradox of black body radiation led to quantum mechanics. The paradox of the Michelson-Morley experiment, which failed to detect the ether through which light was supposed to propagate, led to special relativity. The paradox of the expanding universe's acceleration led to the discovery of dark energy. Each time the universe has seemed to contradict itself, the resolution has revealed a layer of reality more beautiful and more strange than what came before. So what paradoxes of time and space remain unsolved today? The list is long and luminous. The nature of dark matter and dark energy, the unification of quantum mechanics and general relativity, the origin of the arrow of time, the meaning of quantum mechanical measurement, the reality of the multiverse, the nature of consciousness, the reason for the fine-tuning of physical constants, the origin of the universe, and the deepest question of all, why there is something rather than nothing. These are not just puzzles for physicists. They are the questions at the heart of human existence. Because we are not just asking, what is the universe made of? We are asking, what are we? We are asking, does our existence mean something? We are asking, are we alone? We are asking, is there a purpose to the arrow of time, to the low entropy beginning, to the very specific history that led to us? Physics cannot answer all of these questions. Perhaps it can answer some. Perhaps it will reveal that the questions themselves need to be reformulated, that the very concepts of meaning and purpose are features of conscious experience that need to be understood within a physics of consciousness that we haven't yet developed. But one thing seems clear. The universe is not indifferent to these questions in the sense of being unrelated to them. The universe is the source of the questions. The universe is the stage on which they are being asked. The universe is, in the form of human minds, asking them of itself. And maybe that is enough. Maybe the fact that the cosmos has, through 13.8 billion years of expansion and cooling and star formation and planet formation and chemistry and life and evolution, produced beings capable of standing at the edge of the cliff of understanding and asking, why? Maybe that is not a small thing. Maybe that is the most extraordinary thing that has ever happened in the history of the universe. Now, here is something to sit with as we begin our final approach. The universe is not static. It is not a machine running on fixed rails to a predetermined end. It is a process, dynamic, creative, evolving. The laws of physics govern its broad strokes, but within those laws, an almost unimaginable variety of structures, patterns, and histories can unfold. And we, conscious, curious, troubled, wondering, are one of those structures. A temporary but exquisitely improbable crystallization of the universe's capacity for self-organization and self-reflection. Every time you look up at the night sky and feel small, you are having an accurate response to accurate information. The universe is unimaginably vast, and you are unimaginably small. But every time you understand something about the universe, every time one of these ideas lands, every time a paradox opens up a new perspective, every time you feel the particular mixture of awe and vertigo that comes from staring into the deep, you are doing something that may be almost unique in the cosmos. You are being a mind. And minds, whatever they ultimately are, whatever the physics of consciousness reveals them to be, are the only things in the universe that can transform the universe from a collection of facts into a collection of meanings. The facts of the universe, the expansion, the fine-tuning, the quantum weirdness, the black holes, the dark matter, the gravitational waves, are just facts until a mind encounters them. And then they become wonder. They become questions. They become paradoxes. They become the driving force of inquiry that may one day lead us. Perhaps not us, but our descendants, biological or digital or something we haven't imagined, to answers that make the current state of knowledge look as primitive as the medieval understanding of the stars. What will those answers look like? What will it feel like to understand, truly understand, the nature of time? To know whether the block universe is real or whether time genuinely flows. To know whether the universe is one or many. To know whether consciousness is fundamental or emergent. To know why there is something rather than nothing. We can't know from here. We are inside the paradox, looking out. We are inside the story, unable to see the ending. We are inside time, unable to see it whole. But here's what we can do. We can keep asking. We can keep looking. We can keep building the instruments. The telescopes, the particle accelerators, the gravitational wave detectors, the quantum computers, that extend our senses into realms our biology never evolved to perceive. We can keep following the mathematics, even when it leads to places that make no intuitive sense, trusting that the universe's mathematical structure is a genuine guide to its nature. We can keep arguing, debating, publishing, testing, failing, and starting again. Science, at its heart, is not a collection of answers. It is a method for navigating uncertainty. It is a way of holding paradox, not resolving it with false certainty, but living with it, probing it, learning from it, being changed by it. And the paradoxes of time and space are the greatest of all paradoxes, because they are not about remote galaxies or exotic particles. They are about the very framework within which everything exists, the when and the where that contain every what. They are about the stage on which the entire drama of existence is played out. The ground beneath your feet is not solid. The moment you are living in may not exist in the way you think it does. Time may be an illusion or a necessary feature of consciousness. Space may be granular or holographic or a projection from two dimensions. The universe may be one or infinitely many. You may be a unique and precious consciousness in a vast empty cosmos, or one of an infinite number of near-identical copies in an infinite multiverse, or a temporary Boltzmann fluctuation in an eternal void. You don't know. Neither do I. Neither does anyone. But here, right now, in this moment, this mysteriously thin, possibly illusory, definitely passing moment, you are aware of these questions. You are holding them. You are feeling their weight and their wonder. And that is something. That is perhaps the most extraordinary something that the universe, in all its impossible, paradoxical, magnificent vastness, has ever managed to produce. The clocks keep ticking. The universe keeps expanding. The black holes keep evaporating imperceptibly slowly in the cold dark of intergalactic space. The gravitational waves keep spreading outward, carrying the echoes of ancient catastrophes, growing fainter and fainter against the background of cosmic silence. And somewhere, on a small rocky planet orbiting an unremarkable star in a galaxy of 400 billion, a mind is asking, why? The answer, if it exists, is out there. And we are only just beginning to look. But the journey, this particular journey, through the most mind-bending paradoxes of time and space, is not over. It has only just reached the end of what we currently know. Beyond this point, the map goes blank. And there is nothing more exhilarating, nothing more terrifying, and nothing more quintessentially human than standing at the edge of the map and wondering what lies beyond. What do you think is out there? What do you believe? What do you hope? What paradox of time and space keeps you awake at night, staring at the ceiling, with the strange and wonderful sensation of a universe that is too big and too strange and too real to ever be completely grasped? Keep that feeling. Cherish it. Because that feeling, that particular mixture of confusion and wonder, of smallness and significance, of not knowing and desperately wanting to, is the feeling of a mind that is genuinely alive to the mystery of its own existence. And there is nothing more rare, nothing more precious, and nothing more worth preserving in this cosmos that we have barely begun to understand.